Kinetics 2. Okay, so in this lesson, we're going to cover what's called the integrated rate law and half-life of reactions. So don't let the term integrated rate law freak you out. The calculus has already been done for you. But what we should remember is that we already know that finding rate equals how change in concentration of a reactant occurs with respect to a change in time. And then we also wrote the overall rate of a reaction as rate equals K, which is a constant, times concentration of that reactant. And that is how we can determine the rate of either an individual reactant or the overall reaction. And then, of course, this was raised to some power that represented the order of that reaction. So this expression can be integrated with calculus to produce this guy. And you don't have to know how to get from here to here because this guy is on your formula chart. So on your formula chart, you will find natural log A of T minus natural log A. This symbol means not or initial equals negative KT. So where bracket A naught is the initial concentration or the concentration where time equals 0, and A sub T is the concentration after some period of time. And of course, T would be whatever that time period was. So you can take this first order integrated rate law and rearrange it just by moving some of the variables around. And this is kind of useful because if we put it into this order, then now we have y equals mx plus b order. And what this means is that if I plot natural log of a at some time versus time, it will give me a straight line for that first order reaction. So if you recall, when we plotted straight up concentration versus time, if we got a straight line, that meant 0 order. Now we know we have a first order reaction if we plot natural log A versus time. And so you can use this to, one, either graph data for yourself to determine if it's 0 first, or in a moment we'll learn about second order. Or if you're given a graph and you get a straight line under one of these conditions, you should be able to recognize that that means first order. So again, if on the y it plots natural log A, and then on the x, this is plotted against time, if this generates a line with a negative slope, you know that is first order reaction. This only happens for a first order reaction. It was a straight line if it was concentration versus time for 0 order reactions. So an example, let's say we have this reaction, A produces B plus 2D, and we want to find the rate law, the rate constant, and the concentration of A at time equals 500 seconds, which is not part of this data table. So we can extrapolate that from the integrated rate law. And then we're provided this graph. And so we get some information just based on the fact that they gave us this kind of generic graph in this data table. I'm going to attach a second video where if you were not provided this graph, how you could use the data table to determine the reaction order. So that will be a supplementary video to this set of notes. Okay, so the first thing we got to do, we got to find the rate law, and we know a couple things. We know that since they gave us a graph where natural log A was plotted versus time, and we got a straight line from that, that this is a first order reaction. We also know that A is the only reactant, and so we can generate a rate law from that. Rate equals K. A is the only reactant raised to the first power because it's a first order reaction. Next, we're going to find K, and to do that, we're going to use data at time equals 0 and some other time and that integrated rate law. So just plug it in. Solve for K, so rearrange by moving the negative sign over to the other side and divide through by T. I'm going to go back to that data table and I'm going to pick one of the values that was provided to me and plug it in there. And then I'm going to pick whatever the initial concentration was and plug it in for A naught, or initial concentration, and then just solve and simplify. And we find that K equals 3.3 times 10 to the negative third, S to the minus 1. And lastly, finding concentration of A at 500 seconds. We use the data at time equals 0 and then plug in 500 seconds, and we're going to solve for concentration of A at that particular time. So in this equation, the term we're solving for is what is the concentration of A after 500 seconds. We know what the concentration of A was at time equals 0. We just figured out what K was, and we know that time, we're going to plug in 500. So just plug in all of those values and then simplify and solve. And we get that the concentration of A after 500 seconds should be 3.8 times 10 to the negative third molar. So one other thing you might be asked to do is to interpret what would happen if we manipulate the temperature. And we haven't talked too much about temperature yet. That actually comes in the third lesson, the third set of notes for this unit. But think about what temperature measures. It measures kinetic energy. And as temperature increases, the kinetic energy goes up. As temperature decreases, the kinetic energy goes down. And in order for a reaction to happen, things have to, molecules and atoms have to collide with each other or collide with the walls of the container in order to break apart into products. And so as kinetic energy increases, the number of those collisions that happen also increases. Or as kinetic energy goes down, the number of collisions that occur would go down. So here's a plot of a first order reaction. And I know it's first order because I have a straight line when natural log AB is plotted against time. So we have a first order reaction. This is the graph of that occurring at 25 degrees Celsius. And we're asked to sketch a line that shows what we think would happen if we ran the exact same experiment, but we did it at a lower temperature. So hopefully you can recognize that if we're running the exact same experiment, our line should start at the same concentration because we haven't altered the concentration. The initial concentration should be the same. So our line should start here. But if we lower the temperature, that means the rate is going to be moving slower. And so how does that translate in terms of how natural log AB changes with respect to time? We get the fact that AB decreases less rapidly. It's going to change less rapidly because we lower the temperature, therefore slowing the rate. And so that would be sketching, adding that graph on top of there, sketching what would happen if you lower the temperature. This was a question on an AP exam within the last 5 years. So let's talk about half-life. Half-life is the amount of time it takes for the concentration of a reactant to decrease by half. So if I start with concentration at time equals 0 up here, when the concentration of this is reduced by half, so let's say this is 100 atoms or 100 molar, when the concentration is reduced to 50 molar or by half, the amount of time that took is called a half-life. So a half-life. And keep in mind that this is plotting concentration versus time. One of the things I would hope you'd recognize is that when we plot concentration versus time, if this is a first order reaction, we would not expect to see a straight line. We would expect to see a curved line because straight line is only produced when we plot natural log of concentration versus time. One of the unique features of half-life of first order reactions is the fact that it's consistent. So the amount of time it takes to reduce A at time 0 by half is the same amount of time that it takes to reduce half of A by another half. So these time intervals are consistent. And that's something unique to first order reactions only. So we have a question. Find the half-life for the following reaction. We're given 2N2O5 yields 4NO2 plus O2. And we're given a graph where we've plotted natural log of the concentration versus time. And there's some features identified on here. And so to tackle this, let's first find K. So we can just use some of the information on the graph to determine K. And remember, K, if we rewrite our integrated rate law in y equals mx plus b form, K is the same as negative slope. So to find slope, you can just do rise over run, and then take the negative of this value, and our K is 1.7 times 10 to the negative third, s to the minus 1, or 1 over s. So now we have K. Step 2, we're going to find the half-life. So we just plug it in, and remember, if we're reducing by half, if we start with a concentration of 1, then half of that would be 0.5. So you just algebra a little bit, and we find that the half-life is 408 seconds. Kind of a cool thing is there is a simplified version of this formula, kind of a version where this term is already worked out for you, because natural log of 0.5 minus natural log of 1 simplifies to 0.693. And so for first order reactions, this equation is provided on the formula chart. If you look in the kinetics section on the formula chart, T of half-life equals 0.693 over K. So you don't have to actually go through the integrated rate law. You can just reference the formula chart. But keep in mind that's only good for first order reactions. So what this means is it takes 408 seconds for this reaction to decrease by half. So whatever this initial concentration was, 408 seconds later, we would have half as much of that. So down here is kind of an interesting thing that you should take note of. Half-life is inversely proportional to the rate constant K. So if K is small, that means the rate is slow and the half-life would be long. If a reaction is changing at a slow rate, that means it takes a long time for it to reduce by half. So you could be asked to compare some data like this. Which of the following processes has the shortest half-life? So we're given process 1, 2, we're given rate laws for these things. Both of these are first order reactions. That's kind of important to note to make sure you're comparing apples to apples. And I know it's first order because they're both raised to the first power. And then I'm given my Ks. I got K of the first process is 428 minutes to the minus 1. K of the second process is 296 minutes to the minus 1. And I want to know which one gives me the shortest half-life, which means I'm looking for what has the fastest rate. So just looking at these values, the one with the bigger K tells me that I have the fastest rate. Bigger K means fastest rate. So process 1 occurs at a faster rate when both systems share the same initial concentrations, meaning its rate constant has a larger magnitude. Therefore, it would have a shorter half-life. It would take less time to reduce the concentration of AB by 1/2 than it would to reduce the concentration of BC by half. Okay, so what about second order reactions? As a reminder, rate equals how A changes with respect to time, which is equal to KA squared because it is second order. We can use some calculus on that to get an integrated rate law. You do not have to know how to do the calculus. This is provided to you on the formula chart. So this equation is on the formula chart. We can take that equation and rearrange it again into y equals mx plus b form. And that's useful because now m is equal to k. So the slope is equal to K if you take a second order reaction and rearrange it into Y equals mx plus B form. So when we plot a second order reaction, we know it's second order if plotting 1 over A at a given time with respect to time produces a straight line with a positive slope. That is how I can identify quickly that I have a second order reaction if I plot 1 over A versus time. So here's an example. Use the data provided to find the rate law and the rate constant. We have a data table. They've given us a couple graphs to make a comparison between, as well as the reaction itself. Again, I'm going to do a supplementary video that shows you how to take the data only and determine what the reaction order is if you were not already provided these graphs. So one of the first things you should notice is that comparing these two graphs, natural log of NO2 versus time does not produce a straight line. So what that tells us is that this alone does not tell us this is second order. This alone tells us only that it's not first order. So we know it's not first order. So when we look at this guy, 1 over NO2 versus time does produce a straight line. Therefore, this confirms that we have a second order reaction. So since that tells us we got a second order reaction, we also know that there is only one reactant. So when we write the rate law, rate equals K of the one reactant raised to the second power. So now we have the rate law for that set of data. Now we're going to find K by using the integrated rate law, the data for time equals 0 and some other time on that data table, some other point on this data table. Plug it in, solve for K, and we find that K equals 0.52 molar to the minus 1, S to the minus 1, or you could just say 1 over MS. And lastly, data from an experiment which examined the change in concentration over time for a second order process. Make sure you're reading these very carefully. Second order process at 25 degrees Celsius was used to plot the graph below. So we got our graph. We know it's second order, one, because they tell us it's second order, but also because 1 over AB versus time generates a straight line graph. And we want to know what would we expect if we repeated the same experiment at a higher temperature. So this is a little different than the last question we asked. So if we increase the temperature, that's increasing the kinetic energy, which is increasing the rate at which this reaction happens. Things will go faster at a higher temperature. So how would that translate on this graph? Well, first off, the initial concentration should remain the same. But does that mean we have a graph with a steeper slope or a lower slope? If the rate is faster, AB is going to decrease faster. So we would see an increase in our slope. Our slope would be steeper because the change that's happening with respect to time happens at a faster rate.